Okay, people, good evening. I want to begin with the exercises. I've been working on them for the last couple of days, haven't been marking much. The one thing I've noticed is some of you haven't submitted your programs in the examination. Surprising number. I picked up a couple accidentally, and then I started looking at it systematically, and I've got about 30 students that didn't submit some of their programs at all. Got zero. So I'm now going to have to go through all 350 of you and check that everybody has submitted their last program. Okay, so there's a little warning in the final. Don't make that mistake. I can't guarantee that I will find your program. Make sure you submit, otherwise you've got nothing. You've got zero program. Okay, last week we didn't go through some dig, and I still want to leave that for the moment. What I added today was Ackermann, and I'm going to go through that function very briefly, what it does, and that has to do with complexity. I should have done it last Monday, but didn't for the reason I needed that whole lecture for heap, and it would have broken up the lecture. So I thought I'll devote it to heap, and I'll come back on the complexity, and it was going to go in the exercises anyhow for this week. So Ackermann's function, there are two reasons to do it. Basically, one, it's serious and nice recursion, and two, you play with the command line arguments. You'll find that every single problem from now to the end of the course, you have command line arguments or standard in, and of course standard out and standard error. The usual things. No files, just straightforward. What you did for the quiz, midterm, you'll be doing that every time. So by the end of the course, you won't even think twice about it. You'll be, if you continue to program, of course. If you avoid the work, then you will not learn, and you'll find it just as hard in the final exam as in the mid-session. So keep working on that command line and standard in. Okay, so this question asks you to write Ackermann's function. The thing about Ackermann's function is it gets big. So that means, for example, when you look at the last couple of test cases there, Ackermann's function 2,1 and 4,0, they're 5 and 13, and Ackermann's 4,1 is 65,533. And that took my machine about 4 minutes to compute. Now, we're going to have a look in a moment of what's involved there and why it could possibly take so long. The third question will be an array to heap. So it's basically what I've talked about when I talked about roses last week or last Monday, which I'm going to talk about tonight again. So that's about converting something into a heap, and in particular I said, and this is the normal way I do my work, this is how I do my programming. I forget about standard in, I forget about command lines, and I hard code a test case in, and I try and get the program working. And if the program works, then I introduce all of the housekeeping around it and say, well, how do I want to get my test cases working? I need to get all the command line stuff all standard in correct. So I'm using just hard-coded stuff so that I can really compile and run it instantly. So this program here just has hard-coded array called HEAP, which is not a heap because 1, 2, 3, 4, 5, 6, 7 cannot be a heap. Are we all happy with that? We do know that that cannot be a heap. If I ask you that in the final exam, is 1, 2, 3, 4, 5, 6, 7 a heap? You all say no, and you all get 1/2 of a mark or something. Can I assume that? Even if I change it to 1, 2, 3, 4, 5, 6, 7 and 8, you'll still give the answer no. What was that? I have to do something about you. You're too smart. Yes, of course. I'm talking about max heap, and really from the point of view of this course, everything is max heap. It's too confusing to be talking about mins and maxes in the one sentence or in the one lecture even, because you got to every time say it's max. So always max heap. I promise you there will be nothing but max heaps right through. And I was actually thinking, interestingly, about giving you an exercise of doing a min heap just for the interest's sake, but I think it just confuses. It doesn't help. You don't learn anything by doing it. You can just potentially confuse you. So everything's max heap. But indeed, 1, 2, 3, 4, 5, 6, 7 could be a very nice min heap. 7, 6, 5, 4, 3, 2, 1, of course, would be a fine max heap if I do them in reverse order. Okay, so the idea is here, given that array, convert it into a heap by fixing it up, fix up, calling fix up. So it's not hard. In fact, it's quite simple. It's just you've got to get the programming right. You've got to get the looping and things. Okay, the first thing I actually ask you is, I say at the top here, before you commence this exercise, do the following. By hand, make a heap from the numbers 1, 2, 3, 4, 5, 6, 7. Make a heap from the numbers 1 to 7. Do this by inserting each element in turn into a growing heap, starting with an empty heap. When finished, flatten the structure so that you can see what the heap looks like as an array. This is your test case. 1, 2, 3, 4, 5, 6, 7 is your input, the fixed array, and then when you print it at the end, it should come out into a heap structure. All right, let's do it. We'll do it together. If I come in with an empty heap, I have 1. That is my root node. I have to apologise to the people in Webland who are going to be listening to this who can't see the blackboard, of course. So they'll just have to understand what I'm writing on the blackboard, and I've written down 1 node, if you like, a circle with 1 in it. That is my heap. 1 node, it's a perfect heap. Now I get 2 coming in, it becomes the left child. But that's not a heap. I have to fix up. Okay, so every time I add a character, I call fix up. And fix up, if you remember, knows where the parent is and checks the value of the child with the parent. And if they're in the wrong order, it does a reversal, a swap. 2 is greater than 1, so that's wrong. And I have that's for chalk. So that becomes 2, 1. We've got a good heap now. Next character comes in automatically by CTP, the complete tree. It's got to be a complete tree. 3 comes as the right child. Is that a heap? No. 3 is too big. 2 is its parent. 2 comes down. 3 becomes a new parent. Next node comes in, next element comes in, automatically becomes the 4th node, left child, fills in from top to bottom, left to right. 4, is that in the right position? No. 4 is too big, parent is 1. Child can't be bigger than the parent. So 4 and 1 are swapped by fix up, so this becomes 1, that becomes 4. We've got to go all the way up the tree, fix up, and then checks the parent of the parent, this time the grandparent with the parent, sees that it's wrong again. So this becomes 4, this becomes 3. Next one comes in, 5. It's wrong, it's bigger than the parent, swap them. That's bigger than the parent, swap them. Next one comes in, 6. Bigger than the parent, swap. Bigger than the parent, swap. Next one comes in, bigger than the parent, swap. Bigger than the parent, swap. We're finished. Okay, I could keep on going. I could put 8 down here and then do a fix up. 8, 1, 8, 4, 8, 7. Swap them. So 8 will go to the top. And 9, 10, I'm assuming it in order. I've drawn that way. It's a picture of a tree. Computers don't know anything about trees. Computer's not doing that. The computer just has an array. So the computer is just working with indexes in an array. So what the computer started with is an array 1 to 7. That's all it's got. Now, well, yes and no. It's got that and it hasn't got that because it initially as that, empty. And then you put 1 in, you read the first character, 1, first number, 1. And then it does a fix-up of 1 on itself. There's no tree. And then, that's okay. So then you put in 2 into the array, and you call fix-up. And the fix-up routine, if you look at your notes again, 2, being the child, we'll look at for its parent, which is half of 2. 2 divided by 2 is 1. It says they're the wrong order, so what it does a swap. So I'm doing exactly that, but now I'm doing it as the computer is doing it. It's working in the array. Now, I'm happy that's heapified. I add the 3. That's wrong. I've got to replace, I'm bigger than my parent. My parent is 3 divided by 2, 1. So my parent is too small. I've got to swap with my parent. Finished. That's my third number. Add a new element. So on the fly, as I add each element, I'm heapifying, which means I'm putting that element in the right position by calling fix up. Fix up says, who's my parent? I'm 1, 2, 3, 4. 4 divided by 2 is 2, so my parent is 1. I'm bigger than 1, so swap. Now I'm happy. No, I'm not. 2 divided by 3, 2 divided by 2 is 1. That's my parent. So 4 and 3 have got to be swapped. Now I'm happy. Okay, there's my heap for 4 elements, 1, 2, 3, 4. And I had 5 and 6. So you see it's happening on the fly. I don't put it all into an array. As I read each or input each from wherever it may come from, I heapify as I'm building. The crucial thing here is as each new element is put into the growing heap, the previous elements must be heaped. You cannot add an element to anything which is not already a heap. The algorithm, if you like, when you check with your parent and your grandparent, etc., that heapify algorithm, that heapify function works because everything before what you just put in is already been heaped. If you break that rule and try to do something, you try to cheat, which I'm going to get to in a moment, you'll find that it doesn't work. I'll show you in a second. So this is the algorithm. Now, of course, and what you will expect is the program here, array to heap, converts the array, 1, 2, 3, 4, 5, 6, 7. Well, what's that look like? I'm not sure if I actually did. So, 7, 4, 6, 1, 3, 2, 5. 7, 4, 6, 1, 3, 2, 5. That is what my output will be. Now, you will look at that and say, is that a heap? 1, 2, 3, 4, 5, 6, 7, or 7, 6, 5, 7. I can see the order there, but that's a partial order. That's a perfectly good heap. That is wonderful stuff. It's magnificent. But my God, you have to look at that twice to convince yourself that that really is so wonderful. That really is something that satisfies HOP and CTP. The heap order property, and it's complete when considered as a tree. And that can be considered a tree. And there will be other trees, of course, on those numbers. which would also satisfy hop and CTP. So in this program, I have the array. I just have to walk through that array. I start with 1, 2, 3, 4, 5, 6, 7. I start with 1 and I pretend I don't have it, if you like. And as I get to each one, I call fix up, which swaps the earlier elements, if necessary, to keep it intact. So initially that's my heap, and that my heap, and that my heap, and everything to the left is my heap. Now, in the next question, as you would expect, and this is why it's so beautiful, I'm converting args to heap. That means this 1, 2, 3, 4, 5, 6, 7, I don't have them. I've just got args. So I've got argv. And argv, well, it's coming in. As I read each one, I can heapify, or I can fix up my growing heap. Okay, I can process the arguments in argv, command line. I can process them as I read them. Now, of course, this program, the third or fourth program in the exercises, I ask you, get rid of that fixed array. 1, 2, 3, 4, 5, 6, 7, and write the program for command line argument. So I run the program and say it's called args. It is called args. No, I won't write that down. It's called args2 array. When you run it, ./a.out, you give it the command line arguments. 1, 2, 3, 4, 5, 6, 7. 7 command line arguments. And it should do exactly the same thing. Produce this in flattened form. Okay, so that's this program. But this program, the args to heap, that doesn't have an array. And immediately a little light will come up in your head which says, wonderful, I can do a malloc. Okay, so how big should the malloc be? Well, we assume that every argument is going to be a good number, so I might as well make the malloc the number of arguments I've got. So as each one comes in, I put it into my malloc area. I malloc the right size. I've got a pointer, and I can put the number into the memory, and I can do a fix up of that piece of memory. It's really nice, but it's a bit fiddly. It's really good to have first got working the array to heap program. When that program is working, you've got the process. Now you've just got to get the window dressing, you could almost call it, which is getting the arguments from the command line and getting the malloc and working with the pointers, the malloc pointer. In that array to arg program, you've got an array. And realise one thing, which will not have been obvious to you. I go to the lectures quickly. Can I get back here? I think I can get back here. We can do this pretty quick. When I go and have a look at my, which lecture was it? Heap data structures. And I look at fix up. This is what it's all about. Fix up does everything for us. Fix up is gold. Now, the thing that should come into your face, hit you in the face, is, my goodness, I've never seen so many arrays before in my life in one program. Oh, unclean. All those arrays, look at it. Array, heap child, heap child, heap child divided by 2. Now, I ask you, or I tell you, in that question, args to heap, I want it array free. Okay, we're in this array free zone again. Now, that means you need to Get rid of all those square brackets. And some of you may balk at that. It's easy. Okay, that's the exercise. And when you do that, I think a lot of the fear that you have, when you get that program working, some of you will still have quite a lot of fear about this array stuff and malloc and pointers. When you work out how to do that, it's trivial. Those that know already know. And you just have to really be aware yourself, oh, it's easy. And when you get that awareness, I think that you'll find that this program, this one particular program, args2array, will help you a lot in the course. A lot of things will sort of come together. So please do it, that one. And you really can't do it without having done the previous exercise, which is the array to heap. So array to heap, and then args to heap. Okay, they're very important programs. And I couldn't resist. Cheap. Okay, this is now character heap. And just to keep you on your toes, I say, let's do this character heap program. It doesn't actually bring anything into this because it's basically the same thing, except for integers. 1, 2, 3, 4, 5, 6, 7. I've got characters. Well, no, I haven't got characters. I've got alphanumeric characters, which means no brackets, no semicolons and commas. I've got the lowercase, uppercase characters and digits, those three classes. And they are the only things that can appear on the command line in single form. So you can't have two characters next to each other, just one character. So you then have to be able to parse the command line and say, you want one character, and it's got to be alphanumeric. And if somebody puts a bracket or a comma or a semicolon or a hash character, that's ignored. It doesn't come up with a usage command, it's ignored. I say that here. So it's a good case, a good exercise in reading the question. That's the first thing. Reading the question, understanding what it's wanting, and then implementing it. Okay, and the question here I'll show you there through quite a few. So, red rover, move over. It's ridiculous. They've got to be single characters. So you see the ampersand, the add character, rubbish. No input argument, rubbish. Do nothing, just do nothing. ABC, fine. Convert ABC into a heap, CAB. The C is the third character is entered, A and B. Yes, A and B are okay. The B and the C get swapped, and that's why it ends up CAB. Then one egg, then E, F, G, H, they get ignored, those strings. And then you have ABC again. So the character arguments that are not single character alphanumeric get ignored. So you don't have to worry about error messages. Keep it clean, robust. And then I say one egg, and there you see the result, thin heap for one egg. And that should immediately raise in your head, we've had this before, what does it do in fix-all when it has to build a heap from characters which are digits, as against lowercase, as against uppercase? How does it compare a little a and a big A, or a 1 and a little a, or 1 and Z, big Z and little a? How does it do comparison? Well, it uses, and that's why I've got it down here, just to make sure you're aware of this, and don't forget it, ASCII codes. That fix-up compares elements, and if they're integers, you know what it's doing. When it's characters, you've got to hesitate. You think, oh, what's it doing? It's comparing ASCII codes. And if you type ASCII into any CSE machine or any Linux machine or Unix machine, ASCII will actually tell you all the codes for the whole full character set, 255 of them. And you'll see that the lowercase letters are bigger than the uppercase, which are bigger than the digits. So that's the order you'll get in the heap. So one is that true? No, yeah, one is lowest because it's got the lowest ASCII coding. And if there had been a capital E, that would have gone to the top. But little e is going to be under G. And then I give a whole random string there, and just you see things. Okay, that's a nice little exercise. And if you, the one thing that may, again, this is a nice exercise for another reason. I say it even there, alphanumeric, I've got to pick up character sets and horrible. If you look at the C reference card, you'll see under ctype.h, page 2, you'll see one of the little functions you can call is called alpha. Is alphnum, forgotten, something like that. One of many cases. And it's a function which will tell you yes or no whether something is alphanumeric or not. So you just have to call that. Okay, it's very simple, really simple. You get it right. And you can make a lot of work out of it to get it right if you don't think for a moment. And in the exam, that's why I want you to be aware that that card is there for you to use. So get used to looking at it, knowing where everything is, and be comfortable with it. Sort of part of you. You know where everything is. Oh, how do I do that? What's the alpha? Is alpha? So I've already forgotten, because you don't do it every day. And then, oh, that's what it is. And then you just plug it in and she works. Okay, so it's good practice. So they're the exercises for this week. Spent quite a long time on getting those right. I won't put up the solutions for a while to give you time to do them, because they're absolutely worth doing. Now, let's go back to, just want to finish off the heap data structures. I was a bit rushed at the end last week. I went through 1, 2, 3, 4, 5, 6, 7 again, so you can see how we do, how we make a heap as the data's coming in on the fly, as it were. All that is this section here, comparing heaps with normal arrays, and what we need to do. Oh, sorry, no, it's converting an arbitrary heap array into a heap. We use fix up, or you can use fix down. But be careful that you don't get the wrong one. That's what I just want to spend a few minutes on now. And we started last week with roses. No idea anymore where I got roses from, what I was thinking at the time. I'm not even sure it's a good example. I think of a lot of other words. I mean, a nice word would have been maybe heap, or student, or comp, or something. But roses? So, okay, I've got roses. Now, roses is a string. Just like 1, 2, 3, 4, 5, 6, 7 is sort of a string of numbers, if you like. Now, roses, 5 letters. If we picture it as a tree, we draw it as a tree, the computer doesn't do any drawing, we see that structure there. R at the top, position 1. Position 2 is the O. Position 3 is the S. Position 4 is E, and position 5 is another S. That's what it would look like, and that is clearly not a heap. So how can you make something like that heap? I'm repeating a little bit now, but I'm working towards something. Well, we repair, what I call repair. I shouldn't introduce new terminology because it's not really repairing, but I heapify as I read the data. Okay, so as each new number or character is read, I call fix up. So I read the R. That's my first character, just like I did with the number 1. It's a fine heap. 1 is a fine root heap, root only. Then I read the O. R is greater than O, so RO is fine. It's a good heap. Then I read the S. I've got a problem with S. S is bigger than R, so I've got to swap S with its parent, which is the R. So S and R get swapped. So my new array is SOR. My array is SOR. Then I add the E. That's fine. Then I add the next S, which is not fine because it's hanging under O. Parent is smaller, so it has to be swapped with that O. So S and O get swapped, and then I've got S in position number 2 and S in position number 1, but that's fine. Child is not bigger than the parent, so that is my finishing tree, my finishing heap. And it reads as an array SSREO. Actually, fix up of location 1 didn't need to happen. Fix up of location 1 did not need to happen. Why? I don't know who's talking. I can't see. Say it again. Yeah, I want something more. That's right, but it's right for a reason. Say something more. What does fix up do? It compares what with what?
Compare with child with parent.
Child with parent. How many parents has the root node got?
0.
So what? You can't compare with anybody. So the while loop or for loop, I've even forgotten in fix up, it doesn't do that element. It just ignores it, if you like. So why even call the function is the point. There is no parent for node 1. Oh, by the way, I meant to say this while I was doing this, but everything what I've just said there, when I create that array, 7, 4, 6, 1, 3, 2, 5, okay, that's my array. Well, that's not quite true, of course. I've got something at the front. So I only ever work with index 1. That thing there, in my programs, I call -999, just to fill it with something. Okay, so that I'm ignoring the 0th element in the array. It's a perfect good array with some number in there which is never touched. Okay, so don't get confused by that 0 element. But that does mean if you have to malloc for a heap, you need one more. So when you malloc for an array, the array elements go from 0 to n-1. They're your n elements. When you malloc for a heap of n elements, the elements go from 1 to n. And you've got 0, so you need n plus 1. I even had that a couple of times, that I did my malloc, a couple of other programs, and I got a seg fault. And it says past malloc area or something like that. What? Impossible. It's a perfect program. I'm right, it's wrong. No, then I look, done it again. Forgot that there's one more in a heap. That's a little pitfall. Okay, back to fixing up. We don't fix up the top element. No, okay, big deal. There's one comparison we don't need to do, so we can fix up just from the second element on. Okay, all right. Now, the other way of doing it is what I call snazzy, is neat, and is where you work backwards and think backwards. You work backwards, so it means that you have all of the elements in the array, and then you go from back to front. So you take the leaf node right at the end, you assume, you don't assume. Don't assume anything. You take the first node and you do a fix down. Now, just think about this. What are we doing? No, I've lost my duster. No, I haven't. It's really interesting, and it does make you think a moment about why is it so? So, if your array has got roses in it, okay, and the first thing is, that program, I've even forgotten, I put a character in there or something like that, some random character. So there's my array. Now, if I'm doing it forwards, My R, I don't even have to fix it up, we already heard. That's got no parent, therefore it's the point. So when I get to the next character, 2, I do a fix-up, which basically means that O's got to be compared with R. Okay, and then I go to the next one, which means that S will be compared with R, its parent. And that's the way you go through it. That's fine, that's thinking forwards. We want to think it backwards. We've got the array, got it now. I can start with this one. Now when I was working left to right, I did a fix-up. And a fix-up checked characters or integers with the parent. So a fix-up sort of worked that way. And it works that way, and this is what I said, that's really important. There's one way to think about it, but it's hard to keep this in your head, is the reason the algorithm works, fix up or even fix down, is that it is based on the premise, on the assumption that everything that's gone before is heaped, is a heap, is heapified, is fixed up. Okay, so that means when I'm here with fix up, that everything before has already been heaped. You think, of course, makes sense. Reading left to right, and as I get to each character, everything before is done. So really fix up, if you think about it, well, fix up is going to the top of the tree. It's fixing up from my current position, I'm the sort of the new leaf, to the root. Okay, to the root. So it's going actually, it's sort of going that way through the tree. It's a sort of an arrow, believe it or not. People in Webland will not be happy with me because they have no idea what I'm drawing on the board. So that's actually what fix-up's doing. And you don't sort of think of it that way. You think, well, you call fix-up as you go left to right, that's fine. But actually it's going the other direction to check that what you've put in is okay relative to what you've done, knowing that what you've done is good. Now, that's one model, if you like, one way. Now, if you reverse it and you start here, you can't assume anything up there is going to be okay. So when you fix down, you're going this way, so you fix down actually works that way. Okay, that's why you've got to do a fix down. Because when you've said, okay, that's my node, do a fix down. Fix down, well, S hasn't got many children. The last node is never going to have any children. And that's the issue, that's the point. You don't have to fix down for the last node. In fact, this next node either. In fact, who's got children here? Until I get a child, there's no point to fix down. I need to have a child. I can't fix down if I don't have children. Childless parents can't be fixed. You understand what I mean? Okay, so let's look at it as a tree. R, O, S, E, S. Childless, childless, childless. We start here. There are 5 elements. We divide by 2. We get element 2, all integer arithmetic here. That is element 2. So you only have to fix down from n divided by 2. Because everything after n divided by 2 will be childless. What a great question that would make. If I could just get it in some succinct form so that your answer I could understand it, because you could, my goodness, make a long explanation of just trying to say something quite simple. Okay, so that's the whole point here. We fix down from right to left. So what I'm doing, let's forget about that for the moment. That's assuming I'm happy to handle the childless cases. Okay, I start with S. All its children have got to be fixed down. That means I check its children. It's got no children. Okay, that's a heap. Now I go to the next node, next element. Its children have got to be fixed down. Well, S is not a child of E. E is as you saw here, here's S and here's E, and they're both children. So it's fine. Okay, so next child, S. So we're over there now. It's got no children. It's fine. I actually only had to start here, but okay, I'm forgetting about that fact for the moment. Now I'm at O. It's got children. And who are the children? E and S. So when you fix down, that element is compared with the two children to make sure it's smaller, and it isn't. Sorry, yeah, and it is smaller. It has to be bigger. So it's wrong. And who is it? It's wrong with? Because when you compare it with S, it's too small, so they get swapped. S and I've already forgot what I got rid of. Oh. Okay, so have I done that right? Yeah. What have I done wrong? Oh, I've got, thank you, very good. Yes, so in fact, O, S, I've done the S, that O, and the child is that S. So that's the O, and that's the S. Very good. Okay, now, I'm happy, it's children, I'm good, well, so I'm finished there. Now, so remember, I am heapifying down, well, fixing down, but I'm actually travelling up. The easy thing to do is to think that you travel up, therefore you have to call fix up. But that is wrong, 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 because you can only fix up or fix in the direction of the data that you have already heaped or heapified. Okay, you must have good data. So when you add something, it's got to be relative to the data that you already got that's been checked. You can't do it relative to bad data, which is unchecked data, which you've still got to get to. And that's the problem with having the whole array. It's all there. When you're just getting them one at a time, when you're reading it in from the command line or something and you're doing it on the fly, real time, then you don't have that, you don't have the idea. You don't naturally say, well, I've got to wait to get the next characters before I can do my heapify, my fix up. I heapify, fix up, against the things I've already read, which of course you've already heaped to as well. So it's all fine. It's just going right to left that the trick or the trap is that you can call fix up when you go right to left. You don't fix up, you fix down as you go right to left. Long sermon, it felt like a sermon, I was actually preaching. But that little bit here, use fix down, and the thing I say in the middle there, fix down at n equals 2 does a swap, at n equals 1 there's no change, your resulting is array is SRSEO, satisfies pop, it's all finished. And we actually didn't need, as it says on the, actually fix down from n to n divided by 2 plus 1 was a complete waste of effort because they have no children. That's just the nature of the complete binary tree. So we could have just done fix down from halfway. Okay, and then that can actually, it sort of means, well, I suppose it means it doesn't really mean much because you still need a loop. It just means that starting position in the loop is not going to be position n, index n, it'll be n divided by 2. Don't get the direction wrong, and here's an example of getting direction wrong here. Fix up, going from right to left, from n to 1. So in that particular case here, I have 2, 6, 1, 4 in that order, and I start at 4. I do a fix up, wrong, but I do a fix up. At n equals 4, no change, because 6 above it is fine. But don't forget, 6 it hasn't seen before. It started at right and going left. So when it's got 4, it can see who its parent is, but it actually hasn't checked its parent before. It's going right to left. So it sees 6, says, okay, I'm fine. At n equals 3, which is the 1, looks at its parent, 2, fine. And n equals 2, which is the 6. Oh, it sees my parent is 2, it's wrong. I have to swap with 2. So 6 and 2 swap. And then at n equals 1, it sees 6, it has 6, it has no parent, therefore it thinks it's finished. So there's my heap. And that's not a heap. Okay? The 4 is wrong. Everybody on board? Everybody sort of see what's going on? How simple it is? But you've just got to be a little bit careful. You don't want to have too much wine or be too tired when you're doing it. Maybe you don't want too much anxiety either in the exam. If you have to work out fix up or fix down. You really have to get that crystal clear in your head and understand when you go right to left, you fix down. When you go left to right, you fix up. Okay. So that's it. That's the end of all of that. Let's, for light relief, you could say, let's do that last bit of program analysis having to do with Ackermann. I like Ackermann. Just to bore you possibly to death, let's have a quick look at Towers of Hanoi. Now, can I get a light off here somewhere? Finish this bit of complexity. This is reasonably self-contained, the Towers of Hanoi. I know you will have had this before, maybe more than once in various courses, so I don't want to spend any great time on it. The only reason to look at this is, and I've ummed and ahed whether I'll even ask you to write a program to do Towers of Hanoi. Does it achieve anything? Really, the only thing that Towers of Hanoi makes it interesting is its complexity and how you can derive its complexity mathematically. That is a questionable exercise for the exam, final exam, by the way. So when you say to me, I don't want so much programming, I want other kinds of questions, be careful what you wish for. Okay, if I ask you one or two complexity exercises, you'll afterwards say, why didn't you just give us programming exercises? I love command line arguments. They're in my DNA now. I've learnt them, I understand them, and now you're going to ask me these technical, horrible questions on complexity. So be careful what you wish for. So here's okay, let's do the Towers of Hanoi a little bit first. I hope we understand there are 3 pins. We have our discs, all the different sizes on one pin, all nicely ordered, and we want to small at the top, big at the bottom, and everything in between in the right order. And we want to move them from that one pin to another pin, say the end pin, with one pin in the middle where you can put the discs on as sort of a temporary buffer. So you have 3 pins and end discs. So if you have, now, okay, that's the game, that's the puzzle. Now if you have 2 pins, a little pin and a big pin, the little pin is on the big pin, so 2 discs, a little disc and a big disc. The little disc is on the big disc. How do we get that from its source pin to the destination pin? We take the little disc off that one pin, we put it on the buffer pin, we take the big disc, we put it on the destination pin, and then we take the little disc on the buffer pin and put it on top of the big pin, the big disc on the destination pin. 3 moves. Little to buffer, move 1. Big disc to destination, move 2. Little on buffer to destination, move 3. Both pins, both discs have been moved from source to destination pin. Okay, end of game. So 2 pins, 2 discs, it's easy. If you're going to have 100 pins, so 100 discs, it'll take you 10 to the 30 moves. Trillions of trillions of trillions and trillions of moves to do it right. It will cost you a long, long time, obviously. So it's a lot of moves. So it really blows up. To solve the problem, it actually, I can remember this when I first had this problem in computer science in the, God, I don't even remember the decade so much anymore. So how hard it was to understand this. And it's so simple, but you overcomplicate problems often. So easy to overcomplicate in computer science, and you can't see the simplicity, certainly of the And the elegance and simplicity of a good solution is just astounding. It just shocks you almost. How simple something that sounds complex. You think, oh my God, there's going to be, how many moves are there going to be? I've already lost it, have I? Yeah. Oh, that number must be a horrible, horrible exercise to even understand what it's trying to do. With that many moves, if that's the number, but what's it actually doing? Well, whatever I'm doing, when I have n pins, what is the problem here exactly? I have n pins, and I've got to get them from that pin to the third pin, from the first to the third, from the source to the destination. And really that problem can be simplified by saying, actually, if I get the top n-1 pins off onto the buffer in some way, which I can't do in one hit, of course, because you can only move one disk at a time. If I get all of the smaller disks, n-1 small, onto the buffer in some way, then I've got just the big disk. I can move that to pin 3. And then I've got to get all those n-1 onto the n disk. They're the three actions, just like when I only had 2 disks. 3 actions are involved. n-1 from 1 to 2. 1 from 1 to 3. n-1 from 2 to 3. Simple. And that's it, that's the solution. And that's hard to believe, how simple that solution. Because what you've done, and this is classic induction, classic recursion, you've expressed the problem, an n problem, in terms of n-1 problem. So if you solve the n-1 problem, you've solved the n problem. And if you've solved the n-2 problem, well, you've solved the n-1. If you solve the n-3, and you start with 0 or 1. And if you solve 1, so you've got 2. You've got 2, you've got 3, you've got 3, you've got 4. So really this simple 3-step process, moving n-1 to 2, moving 1 to 3, then moving n-1 from 2 to 3, is the solution to the problem. And it gives you, in beautiful mathematical form, the complexity too. So here are the 3 moves. The move n-1 disk to the spare, move the remaining disk to the destination, and move the n-1 on the spare to the destination, and you're finished. This is classic divide and conquer. Here you see the disks and the pins, the source, the spare, the destination, and you see the first move here, the blue, yellow and red go to the middle spare, the green one goes to the destination, that's step 2, and then finally you move the red, yellow and blue to the destination, so step 3. So to move, so you give the pins names A and C. The only thing you want to know is the moves that you need to carry out to actually move all of the pins from one pin from the source pin to the destination pin. You don't have to create any data structures. It's only the number of moves that's important. That's very important in this, in the programming. So the complexity now, well, as usual in some sense, play with it first. If we've got no disks, there are no moves. If we've got one disk, you simply move the disk. If you've got one green disk and you've got it on the source pin, you just move it to the destination pin. So if T is the number of moves we need to move its argument number of disks, then T1 is 1. When we had 2 disks, I went through that process, 2 disks to get them from pin 1 to pin 3, pin C, A to C, is 3 steps. T3, when you have 3 disks, you then, well, now we know that to move 3 disks, it's actually a question of moving 2 disks, then moving the last disk, and then moving those 2 disks again. So it's moving the 2 disks, which is T2, twice, and then moving the final disk. They're the 3 actions. So 2 times 3 plus 1 is 7. The same thing, T4 is going to be doing 2 T3s plus a 1 move to get the big disk to the other pin. So these are, if you like, test cases, initial conditions, boundary case, boundary condition, whatever you want to call them. So the algorithm, to do n, you need to know the number of moves you needed for n minus 1. It's 2 times that number plus 1. So Tn equals T of n minus 1 plus T of n minus 1 plus 1. So it's 2 times T of n minus 1. And let's just check that. Well, T1, T2, T3, it works beautifully. You can, and this is where, really, that's almost enough, because you can look on that straight away, 137. My God, you can. And the next one is obviously going to be 15, and then you just, it's all exponential. You can see it happening there. Okay, but if you want to do it slightly more correctly or rigorously, we write Sn equals Tn plus 1. So Sn equals Tn plus 1. We've got an expression for Tn. We expand Tn as T times 2 times Tn minus 1 plus 1. So we've got 2 plus 1s. So we have Tn minus 1 plus 2, or 2 times Tn minus 1 plus 2. And that is, well, take out the 2. We've got 2 times S of n minus 1. That's our recursion there. So if we now unroll it, we have Sn equals 2 times Sn minus 1 from the previous equation, which equals 2 times S minus 2, which equals 2 times 2 times 2. My goodness, that's wonderfully exponential, which eventually equals 2 to the n times Sn minus n, which equals 2 to the n. Substituting the value of Sn of that into Sn equals Tn to Tn plus 1, we get Tn equals Sn minus 1, which is 2 to the n minus 1, which is exactly what you get up there, 2 to the n minus 1. So 4 minus 1, 8 minus 1, 16 minus 1, etc. Now, you could have guessed it, but this is the rigor. So that's the complexity. Now, there's math there, and it's sort of hard in one sense maybe when you first look at it, but it's actually very simple. In 5-6 lines, and I did it quite verbosely, but it's a nice piece. There aren't too many nice pieces of mathematical rigour, surprisingly, in computer science that you can actually use as benchmarks. This is a benchmark of complexity. If you want to see a beautiful derivation of a complexity argument, this is it. Towers of Hanoi is exponential. Here's the proof. And there's not often in computer science you can do that so neatly in so few lines. Okay, so the whole premise we started with was this algorithm which says you twice move n minus 1 disks with 1 extra disk move. So there are 2 times n minus 1 moves of n minus 1 disk plus 1. Now that insight, that thinking pattern there, thinking idea, was actually what led us to a proof of the complexity of the Towers of Hanoi problem. So that's 2 to the n, exponential. We know how horrible that is. But it's nothing compared to what Ackermann can do to us. Ackermann is such a simple function. It has 2 degrees of recursion, m and n, and they both decrease in this weird way depending on m can be 0 or n can be 0, and if neither is 0, then you reduce m and n and you call it again as a second argument. Ackermann itself has its own argument kind of thing. So it's this weird recursion, and it's very simple, and it's unbelievably complex. The performance, it only uses addition and subtraction. It makes exponential look like child's play. It makes exponential look very slow and well behaved. It's far, far, far worse than exponential. It is in a sense unlimited, boundless recursion. Not in the sense of exponential, which says if you increase n by 1, you multiply the search space by 2. Okay, so when we went from 5 discs to 6 discs, the number of moves required is another factor of 2. We move one more disc, we double the number of moves. Another disc, we double it again. Factor of 2. That's exponential, classic exponential. With Ackermann, all right, what's the complexity, the big O, of Ackermann looking at those numbers for m equal to 0? Someone? What do you see in the numbers? What is it? What's the pattern here? It's what? What's the number? What's the word? Do I have to tell you what its first letter is? What is it? What do you see there? N equals 0. What is that? Yep, linear. Isn't hard. I was going to say first letter is L, and I hope you would have gotten it then. Okay, it's linear. 1, 2, 3. So n equals 4. It's 4. It's 4 or 5. Linear. Linear doesn't mean it's got to be exactly the same. It just means that it's constant. So you increase n by 1, and the number, the solution increases by 1. It's 1 to 1. Okay, so it's a rate. It's not the value. It's the rate. So m equals 0. It's linear. M equal to 1, what is it? It's the rate. What is it? Come on. What is it? It's linear. What is it when m equals 2? Is it a geometric progression or is it arithmetic? Arithmetic. It's a constant increase. So 5, 7, add 2 every time. It's linear. Linear is just a simple addition of a constant. That's what linear is. M equals 3, what's that? What is it? What was the word? Geometric. But what is it? What do you actually see? That we have 13 and we increase n by 1 and we go from 13 to 29, if you like, from 15 to 30. And then we go increase it again by 1 and we go from 30 to 60. So what is that? It's exponential. That's what I'm looking for. M equals 0, m equals 1, m equals 2 are linear. M equals 3 is exponential. You double, that's why I went through that little spiel. You increase n by 1, you double the search space, the number of things you've got to look at. The solution that you've got to search for is going to be in a space of double the size. You increase the number of discs in Hanoi by 1, you double the size of the problem, the number of moves you need. Increase it by another 1, double it again. So it's 2 to the number of discs. Okay, 2 to the number of discs, 2 to the, 13 is 2 to the 4, roughly, and then 29 is 2 to the 5, and then n equals 3 is 2 to the 6, approximately with a constant. Is it doubling going on? That's what exponential is. Well, I can see that. You're going to have a lot of fun in the final exam. I think we're going to have very little bit of programming in the final exam. I see all sorts of questions I can ask you to make the people who don't like programming very happy. My goodness, I can give you all sorts of series and say, what is it for big O? The answer to big O is never geometric or arithmetic. I asked you that so that to get you to understand that it's the rate of progression. Are we adding a constant or are we multiplying by a factor? You multiply by something, you double, multiply by 2, that's not constant. You're not going from 13 to 29, there's 16 in there. Have I done that right? It's not 16 from n equals 2 to n equals 3, it's twice that. And it's twice that again from n equals 3 to n equals 4. That's exponential. It's a factor, it's a multiplicative factor, it's exponential. Okay, so then we have, of course, n equals 4. And I've used a star star as the exponent. So we see at n equals, for m equals 0, n equals 0, we see 2 to the 2 to the 2. For n equals 1, we see 2 to the 2 to the 2 to the 2. And then we see for n equals 2, oh, all these exponents. It's recurring, repeating an exponential for every new n. This is not multiplicative increase or sort of geometric. It's much worse. It's much worse than exponential. What's the word? What is it? What's the word? Does anybody know the word? Nobody dares say the word. Well, it's very good. You're getting very close. I would have given you a good pass mark with that. That's correct. Well, A40, just reading off the table now, is 2 to the 4 minus 3. 2 to the 2 to the 2. The 2 to the 2 as an exponent is 4. 2 to the 4, 16. Minus 3 is 13. 2 to the 2 to the 2 to the 2 is 2 to the 16 minus 3. 2 to the 2 to the 2 to the 2 to the 2. Now that's getting a big number. It doesn't look very dangerous. But that extra factor exponent of 2, we're adding exponents every time now. This is going berserk. That's 2 to the what? 65,000? That's roughly 20,000 zeros. That is a big number. That is mind-boggling. I mean, you're talking about a number there. All of the molecules on the planet Earth, that wouldn't be that big a number. Molecules. Just everything that you're made of, that chair, this lecture theatre, every beach, every animal, person, tree, nothing that can't compare with that number is so massive. And then we have, that's 4-2. Now we have 4-3. I didn't even want to start writing that down because the power, that 20,000 zeros, that's the exponent of 4-3. Now these numbers, and I want you to write a program to do this. And there's a challenge. Well, not really, because it blows up enormously quickly. So all that you can do is 4-0, 4-1 or 3-2, or the smaller cases you can do, but anything past 4-1 is hopeless. So if you look at 4-3, what is going on with 4-3? 4-3 is, look at the recursion, 4-3. 4-3 is 3, 4-2. Looks harmless. So here 3 and 4-2, and 3 and 4-2 is, well, 4-2 is A3, 4-1, and then 4-1 is etc., and then it starts getting bigger, and you find by the time you're finished, it's going to be A equals 3 times A to 3 to the 65,533, and eventually you'll get down to that number there, which is the number I showed you earlier. And the word for it is, it's tetrational. Tetra, meaning 4. Not sure why 4 really. It's not very old. Somebody gave it a name and piece of work, piece of research, not too many decades ago. And because these numbers are ridiculously large and they're all exponents, this is the term of today, this is the name, the thing that you've got to remember today. That number, going back up to the top here, those numbers here, 2 to the 2 to the 2, all the way up, they're called power towers. So tonight you've met power towers. It's a great term, the power towers of 2. So a power tower of 2 is a series of exponents 2 to the 2 to the 2 to the 2 to the 2. You can keep on going for as long as you like, That's Ackermann's function. It's the quintessential power tower. Generates power towers as if they were confetti. So, and the way you normally write that is you use a double upward arrow. So 2 to the double arrow 1 is just 2. One instance of 2, one level. 2 to the upward arrow 2, 2 levels, 2 to the power 2. Upward arrows 3, 3 levels, 2 to the 2 to the 2. Then 4 and 5, and you see already by 5 we've got the 2 to the 65,536. That's 5. We haven't got the 6. 6 is horrible. So you could write that fourth row, m equals 4 row, fifth row, is 2 to the double arrow 3, 2 to the double arrow 4, 5, etc. That's the way you could denote it. I haven't seen it written down that way, but that's what it is in power towers. So Ackermann's function generates power towers of 2. And this is just a whole new ball game that really makes exponential look like child's play. It's a picnic. This is really, really nasty, nasty stuff. And what some people like, what I call it, this is where I saw somewhere that was a mad benchmark that hackers use when they want to bring a computer to its knees. Now, in earlier days, that could be, you could do that. You could bring a computer, you could actually really overload the computer so much it basically would just crash. Today, there's so many protections on memory that you can't do that. But in the old days, it was the classic benchmark to bring a computer to its knees. It's only 10 lines long, very simple little program, and it just goes forever, and it just absolutely takes all of memory, and then it wants lots and lots more, and the whole thing comes to a grinding halt computer. So that's Ackermann's function, with tetrational, and that is, it's what it is. It's incredibly, incredibly bad. Okay, now, that was a brief respite from heaps. Where can heaps lead to? Heaps can be used as data structures hidden in an ADT to give you fantastic performance. What I do now is I'm going to explain the concept of delmaxing, which you could also call delmining if you want to take the minimum heap, delmaxing and insertion. And I'm going to generalize in a way that you would have never thought of the concept of a stack or a queue. A stack and a queue are actually incredibly naive if you think about it. A stack, we have the data in an array, possibly, and we add something to the end and we take something off the end, push and pop. The queue, more or less the same thing. We have this array of data, we add something to the end, we take off from the other end. So we work on different ends. We can add to the other end and we take off the first end. So you just work on opposite ends and it's a queue. When you're working on the same end, it's a stack. That's the essential difference. But think how naive that is, because the fact that they're ordered in a way may not be what you want. There may be other factors which determine which one you want. And if you want to generalize the concept of a stack or queue, you can say, well, I want the biggest number out of the data structure. That's the first number I want out. I don't care where it is in the array, in that array or that linked list or whatever data it is, whatever collection it is, I just want the biggest number. And when I put a number in, I push it, it goes in there, and if I get something back, it better be the biggest of everything that it's got. Now that's a generalization of a stack or a queue. So items are normally processed in the order of arrival in a queue, In a priority queue, they're given this concept of priority, but that's not true in a sense. I always find this misleading, and the name priority, it is a priority in a sense, but there's no priority level as you would get in some kind of access privilege system. It's about size. Size matters, if you like. The biggest number is the thing we give the highest priority, and that's the number we want. And this is what we're doing at the level of this course in any case. So we're after an element which is the biggest or the smallest in the data we have already collected. Like a queue or a stack, the priority queue can be implemented on an array, but can also do it in a linked list. And this is where it actually gets slightly confusing, because many of you, and I think even last week, we talked about this very briefly. Why does the heap, which has children, and that is a tree in concept, when the diagrams I was drawing, they were trees, and that's how we think about them, and we want parents and children, but there are no links. Why don't we implement it as a linked list with two links, two pointers to the children, or one pointer to the parent even? Why don't we do it that way? There's only one good reason, there is one good reason why you don't, and that's purely inefficiency. It is terribly inefficient. It has two great problems. One is massive amount of data required to store all the links. If you have 2 or 3 links, if you have to go up and down, you have 2 links for the children, you have 1 link to go to the parent, and if you have one character, if you only want to store one character, and you have to have 8 bytes for the left child, 8 bytes for the right child, 8 bytes for the parent, you've got 24 bytes of linkages, and you've got 1 byte that you want to record. That's a huge, absolutely huge handicap, a huge weight that you're carrying out. 24 bytes for every single byte that you're storing. Nothing of seriousness can afford that kind of wastage, because those links do nothing really for the data. They're just there so you can walk up and down. There's too high a price. What makes heaps effective is the fact that there are no links. There's just maths. You use the n divided by 2, or 2 times n, to go to the children and the parent. 0 overhead in terms of memory. That's why a heap is effective. It's implemented on an array. I could very easily ask you to implement a heap on a linked list. I may yet do that. I'm thinking about doing it, but I'll have to go through the exercise myself to see whether it's going to be 10 lines of code or 1,000 lines of code. It's got to be doable without too much effort, otherwise it's just not worth doing. So. But it's possible. In any case, here we're looking at priority queues, and we're going to look at the issue of how a priority queue, where we're interested in getting data that is the biggest out of our collection, how you can do that. Not knowing what the ordering is or what the arrangement is of the data. That's the generic case. So we just take 2 operations. We have an insert and we have a delete. The delete is just like a pop. When you delete an element, you get it back. You return it to the client and the element is gone from the data structure. So we delete the maximum. That's the element we want. We don't want the last element in. We don't want the first element in. They're the stack and queue cases. We want the biggest element that we've got. So I've got another kind of data structure that's not a stack, it's not a queue. It's called a priority queue. We want the biggest element. We push elements onto this priority queue. It goes into the ADT, and we get back the maximum whenever we pop. We don't call it pop, we call it del max. I could call it pop max. Maybe that would be a better name. Pop max. You're popping the max. Okay, it's the same. It's this queue stack thing, but it has a slightly different or slightly stronger operation, virtual operation. There are also other things you could do. You, of course, want to be able to create a priority queue and you want to know if the priority queue is empty or not. So what do we do when we're inserting and del maxing? If an ADT is a stack, and we have the notation here, you see that on the top line, consider the input sequence EXA hash M hash hash hash. The hash here is a delete operation where we return that element. So we put E in the data structure. We put X in the data structure. We do a hash. So the first two lines, we put the E in that table. We insert the X, we insert the A, and then we do a pop, and we get the A out, of course. The last thing in is the first thing out. This is your wonderful, familiar stack. And then we insert an M. That's corresponding to the first, second, third, fourth, the M up at the top there, that letter. And then we do a hash, which is a pop, and then we do another hash, which is another pop, and do another hash, which is another pop. So that's a shorthand notation up the top pop there, say insert E, insert X, insert A, hash, a pop, insert M, pop, pop, pop. When we do a pop, we return the thing we've popped off, and we see we return the M, the X, and the A, and those last three pops. So EXAM went onto the stack, and they came back in the AMXE order, just because of the way we pushed and popped. Now, if it was a queue, it's slightly differently. Same idea. When we pop from the other end, of course. So when we have EXA on the queue and we do a pop, we take the first thing off, the oldest thing, if you like. E goes off, not the A. Now it's a queue, so we take the other side off. Okay, so this is all should be familiar to you, so you just get a sense of, okay, there's a stack, there's a queue, we push and we pop, and we get this behaviour, this output of EX, A and M in a particular order, depending on whether it was a stack or a queue. So it's very important, of course, that you get your pushes and pushes right. Your pops and pushes right, that you've got the stack, that you've got the data structure you think you've got, and you've got the right operations on them. Now, if it's a priority queue, we get them out in yet another order. We get them out in the order of maximum. So we put the E, we put the X, we put the A into the data structure, our priority queue, our PQ. Now once they're in there and we do a hash, which is a pop max, we pop max EXA, well, the maximum of E, X and an A is X. It's not E, which was what the push would have done, sorry, the pop would have done for a queue. It's not the A, which is what the stack would have done. The pop for a priority queue gets the X, because it's the biggest. So the X comes out. And then we do an insert M, so we've got EA and M in our structure, in our ADT. And then we do three more del maxes, three more pops for our max, pop max, whatever you want to call it, del max, pop max, for our priority queue, and we get them out in the order of size. So when you've got the three characters E, A, M, the first one that comes out with a del max is M. I don't care where it is, it's the biggest, it's coming out. The next one that's big, the biggest, next biggest is E, and then the final last element in the priority queue is A. So that's the order I get them out. There's no difference in one sense, you're still pushing and popping to this priority queue, you're giving it slightly different names, and you get a different result. Okay, so that's the outside, that's what you're looking at, that's sort of the interface. We're not saying how we get the maximum out, we're not saying how or what we do when we push data in, when we insert data. We sort of didn't say that as well with stacks and queues, because we could have implemented using a linked list. We could do it with arrays. With arrays, it gets a bit messy when you're working at the bottom of the array, because then you've got to make room if you're going to push something to the bottom for some reason. So which way you're working with the array, and it can be a bit messy. So these are things that you work out in the ADT, because on the outside world, the client, all he knows is he pushes and pops and he expects some behaviour. Last thing in is first thing out if it's a stack. First thing in is the first thing out if it's a queue. FIFO. Okay? But with the priority queue, it's just a variation of that. It's the bigger thing that comes out when I do a pop or a del max. Del max is a pop. Now that's the essence of a priority queue. That example is not worth doing. So typically, an ADT allows you to create, insert, delete. Create, push, pop. I think push and pop are better terms. So what we want is, with a priority queue, with a stack or with a queue, we could actually go, oh, goodness gracious me. I should actually think of another. I had a quack for a stack and a queue. I should think of another name to include priority queue. So have a stack queue or a priority queue, and then have some generic set of names for create and pop and push. Here they're called, most unimaginatively, create priority queue, then del max priority queue, which is the pop and the is empty and the insert priority queue. Okay, push, pop, and is empty. Completely equivalent in a sense, notionally equivalent, but of course in practice, del max is a specific, very special kind of pop. Other operations you could have is, for example, update PQ, which is an interesting one, which says change the element value from I to J. Which element, you could ask yourself, which element is, what is I here? And that's what needs to be defined. What do you mean by that? But okay, delete the priority queue completely, just throw it all away, and that means freeing, for example, the malloc that you've done to create the priority queue, that kind of stuff, and you can have two priority queues where you can join them together. So here's an example of a client of such an interface, something that is going to use, like Flavius's survival in that against the Romans, when they're getting people out, shooting each other, and seeing who was going to be the last Remainer, committing suicide basically. That program there was a beautiful example of a circular queue. Here we have another little program, which it could be a stack or a queue, but it's a priority queue. Same idea. I've hard-coded in, as I want to do when I'm starting a program or something, and I don't want to be worried about input-output. So I hard-code in some data, and you can see that's unordered data. And what do? I print the word array. I create my priority queue. I've got that in my interface. I then, for all the elements in the array, I print it, and I insert it into my queue. Little q is my priority queue, PQ. See, PQ is my type, little q is my variable, and I insert that number from that array into my priority queue, my PQ. Then I say I print the word sorted, magically, print it, and then while the queue is not empty, I delete the maximum element. I pop the maximum element. That's another word, remember? Del max is pop, pop max. You think of, maybe you should just call them all pop max and get rid of the word del max completely. Because del suggests that you don't have it, you just get rid of it. I think it's misleading. Pop max is better because you know what pop is, you get it. And of course, you don't leave it behind, you take it out. You don't leave anything behind. So you have to delete it there, and that's natural in the pop. So you pop max that queue, which gives you the maximum element. Well, the maximum element in that list up there is 360. So 360 comes out. Okay, it's one element less. And then I go around again, while. Not empty yet? No. Next biggest element, which is 260, by the look of it. Yep, 360, then 260. 260 comes out. It's gone. It's popped out. I can print it. That's what I do there. Print the number that comes back. So all I'm doing is just popping. But I've got a special pop here for this data structure, my priority queue. Okay? That, if you just think what it's doing, I'm sorting. I've got an unordered list there of numbers, they're all over the place, and I pull them out in order. It's sort of magical, I'm sort of out of nothing, I'm getting something, it would appear. All of this hard bit, if you like, is being done in the ADT, obviously. This del max is actually, this del pop or pop max, this is actually doing something. It's pulling out an element which is the right element that I want. Not the latest, not the earliest, it's the maximum. So there's my client. I've had now my interface up here. I've got my client, so really I've got sort of 2/3 or 1/2 the problem solved. What about the actual ADT? What about the implementation of insert and delmax? Well, before we get on to the implementation, just a couple of things. Is it going to be fast? Is this program going to be terrible in performance, or is it going to be fast in performance? Answer is, in terms of speed, we don't know, because we don't know what the ADT is doing. If the ADT has been programmed by a first-year computer science student, we could be in a lot of trouble. If it's a very sophisticated C programmer, it could be a very, very fast piece of code. We don't know how it's being programmed, what it's doing, whether it's got exponential behaviour, Ackermann's behaviour, or linear, or what it is. Is it going to be space efficient? And that's an interesting one, because at first sight you think, well, what's the issue here? And the issue here is, it's so obvious in a way. Well, look at what you've done. You've got your array. Boom, 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 boom. 10 numbers or something up in an array. You've got an array of numbers. If you had 1,000,000 numbers, array is 1,000,000 long. Now, what do you do with those numbers? You put them on or in your priority queue. And you see that happening in line 12, in line 14. Insert the priority queue. Each one. So your 1,000,000 numbers, your 1,000,000,000 numbers are going in your priority queue. So every number you've got is in an array and in the priority queue. It's a complete copy. It's just a different form. And then you get them out again, you suck them out by popping them in the right order. But you've got 2 copies. And we would prefer not to do that. That is terribly wasteful. You're doubling the space that you need. You're better off doing it in place. Good sorts work in place. So the last thing you want to do is waste your time copying, even if you've got the memory, copying the whole array, mucking around with it, and then giving it to the user. You forget about the copy, in situ, in place, whatever you want to call it, you don't take a copy. So it's inefficient, but it's only inefficient because of the way the ADT and this client work together. This priority queue could be made in place. Just for your information, that this particular implementation of a priority queue is inefficient because it does make a copy, but it's very easy programming. If you did it in situ, it gets more complicated. So that aside, what I'm going to do now is I'm going to show you the implementation of the ADT. Now that implementation, no, it's not that, there are 3 implementations. And each one gives you a different flavour of solution, different kind of solution. And it's a beautiful example of how black box the ADT is, and that the client doesn't know what it's doing. The only thing the client can measure or see or feel is how long it's taking. Assuming that the client had a stopwatch, and my goodness gracious, just did a pop max, del max. It's taking minutes to get me that max. What the hell's going on? Or it says, gee whiz, instantly it came in with a max. How did it do that so quick? Or when I do an insert, wow, it's taking a long time to do that insert because I sent it off to do the insert and it's not coming back. Oh, finally it's done the insert. I now can do the next insert. My God, it's taking forever to do these inserts. Anything, in some sense, is possible. You don't know what's behind this ADT, or behind the interface, what the ADT is doing. And those issues of insert and pop max, del max, are very important. How long do they take? And it depends on the ADT data type, the concrete data type that you've got in your ADT. If, for example, and this is where you now need to think and not sort of look, because if you think conceptually about the data, the concrete, the actual data that you've got in your ADT. Now, it could be a linked list, for example, but we'll put that aside for the moment. Here we're going to have 3 kinds of arrays. The first array we're going to say is let the ADT have just an unordered array. Assume it's big enough. And when we get an insert, we just put it on the end of the array. So those numbers and that other those bunch of numbers, 360, 260, all those numbers, they will just be copied onto another array inside the ADT. The client can't see it, but that's what happens. Of course, if you do that, the insert just adds it to the end of an array. It's unordered. When I ask for the max, I've got a problem, because I'm going to have to search that whole array to find the max and then give it to the user, the client. There's a price there to do a get max, pop max. But to put an element on or in the priority queue, fast. If I had as a concrete data structure an ordered array, that changes things. Because that, when I insert the element then in the ADT, I just say insert, and then it happens somehow, and then the ADT comes back, it's done. But what's it done? Well, it's inserted into an array, but of course it's got to insert it into the right spot. So it's actually each time got to do a search for where the spot is that it has to insert the element. Then it's always ordered. It's a really neat, pedantic, careful ADT. It always keeps everything ordered. So when I want the max, it just gives me the first one. It's all ordered. The first one will be the biggest or the smallest. Assuming it's the biggest because we're doing a pop max. So it can always fast give me the maximum element. But it takes it forever to put an element in every time, because every time if I go them in reverse order, it's always got to go to the end or back to the start, and it's all over the place, it's moving back and forth, trying to find the right order. And you say, come on, hurry up, just insert those few billion. How long is it going to take you to insert a few billion elements? It shouldn't take you that long. But once it's got them in there, it can really deliver the maximum element really fast, because it's ordered. It knows where the maximum is, it just pulls it off, straight off. And there's a third possibility. We have had mentioned two possibilities, two arrays. One is unordered and the other one's ordered. Now the third possibility is a heap. We could have we could have an ADT that is a heap. So what does that mean? Well, it means when we do an insert, oh my goodness, that's how we started the evening. We inserted an element into a heap, we just put it into the end of the array, and we do a heapify. We do a fix-up. And we could put a fix-up into our priority queue, and that means the insert wouldn't have to look for a spot right through the whole array, which is what the ordered array implementation does. We just do the fix-up. We put it at the end of the array and run a fix-up, which takes login time, which is really fast, and it's done. So how do we get the element out? Well, that's what a heap does. The element out is really fast because it's at the top. That's what the heap is. It can give us a top element really quickly. But of course, when we take the element out, we're taking out the root. We've then got to do a heapify to get the data structure right again. So we've got to look after the heap. We've got to keep it a heap. So there's a bit of work there in doing a pop max. There's a bit of work in doing an insert. They're both log n. It has massive advantages compared to the ordered solution and the unordered solution, which both have major costs, either in the insertion or in the deletion phase. Now, that's basically all. I just mentioned everything, or told you everything what you need to know about the three implementations. Here is the PQ unordered array, UA. And you see here data structure here, which is number of items, maximum size. Max size is there just because you've got to give a finite size. It's an array, and we don't want to muck around with mallocs and realloc and stuff like that. That's not what this is about. So we just want a fixed size array. That's the size there, max size. We can set that at the start, and we've got to work within those bounds. I'm not interested in things, there's a malloc happening there, of the size of the structure, and a malloc here of the size of the struct and the size of the array itself. Okay, they're being set up here, and then we're setting up number of items as 0, the max size which we're going to store just in case we reach the end, of course, with an insert operation. So we need to know the max size. These are all housekeeping things. What's important is when we do an insert on an unordered array, what the insert does, it puts it to the number of items. That field in that struct tells us what the last element is that's been put on into that array. So it's a pointer, if you like, or an index. It's an index of the last element that's been added. So you can always add a new element. It's really simple to add a new element to the end of an array, and who cares what it is, if it's big, small, or in the middle, because it's unordered. UA is the ADT, it's unordered. And the number of elements, the number of items, increases by 1. When you've got to do a delete, however, you're going to have to pay the price for being so sloppy and not knowing where you're putting things, because you need to do a linear search. That means the bigger the number n, the longer it's going to take you. Linear search here from 1 to last, where last is the number of items minus 1. Line 50, number of items minus 1, that's last. The loop goes from 1 to number of items minus 1, and you compare everything with what you assume is the max as the first element, and you find the maximum. Typical linear search. When you found the maximum, that's the one you return, store it. Retval is array max. Then you overwrite it by the last so that you fill the hole, so you don't have any holes in your array, and then you decrease the number of items. Okay, so this deleting, this del max, give me the maximum element when it's an unordered array. Easily just put it on the end when you insert, and when you delete it, you find the maximum element, you return it, but you call it retval, copy it, you then overwrite it by the last element, fill up the hole, and that's it. And then you decrease the number of elements because the last element no longer exists in that sense. It's been copied to the max position. That's it. So, and that's the end of the story really, because the is empty doesn't change no matter what you do. It's is it empty or not, number of items 0. So, using that ADT called PQUA, unordered array, and you put it with the client, PQ sort, and it works like a charm. And it comes back with the del maxes come out with the maximum. Oh, Wetland is going to be upset with me again. Okay. All right, so let's quickly move and go through the ordered now. The ordered here, OA, ordered array, same structure, same create, number of items equals 0, max size equals size, 2 mallocs happening here, and then I do the insert. Now when I insert now, because it's ordered, I've got to insert it in the right spot, so I've got a lot of work to do. I've got basically a linear search, because the new element that's coming in may be the very last, or maybe the first. I've got to find the right spot for it, and I've got to make room for it. It's got to be an ordered list. I'm very particular. I'm very neat. So here we have, for I equals 0 to last, we check whether the array element is less than IT, the element that's coming in, the element's being inserted. So when we find the right position, okay, we go one too many. Oh, we found the right position. We have to move everything up, and then we've got to plug the new fellow in. God, what a lot of work. I've got this array, fixed array. I found the maximum element. I want to pull him out. It's ordered. I just can't plug something on the end of it to become unordered. So I've got to pull out the maximum element. I've got to split the array, make room, put the new element in, and we'll move them all up and make room for the new element. That's what I've got to do. Split the array in a sense and move everything in the second half up. So that's what that does there. And the del max, well, it's ordered. So the maximum will always be, in this particular order here, the maximum is going to be at the end. So pulling it out is snack easy. It's at the end because it's an ordered array. And then I just reduce, of course, when I reduce the size number of items. And is empty doesn't change. And I can run it with the same data. Instead of PQ UA, it's now PQ OA. And it works like a charm. Compiles beautifully. Okay, they're the two naive, boring ADTs. Now, the third possible ADT, I compare there, let's not get into that. Just summing up then, I've got the ordered versus the unordered, And the implementation, the two rows, ordered and unordered. The insert take is linear, and the delete, when it's ordered, is constant, and and the opposite way around for unordered. So either solution will give you a linear behaviour, which is bad. It's bad for sorting and searching. Hence we have poor performance with either insert or del, depending on which way we go. Can we use a heap to implement a priority queue? Well, we certainly can, and here's the heap. Now, we have exactly the same priority queue data structure. You see the number of items, the actual array here. We have the same create happening here, 2 mallocs, number of items equals 0 when we create, maximum size equals size. We return the queue, we return the data structure to our client, who can insert and delete max or pop max from that data structure. And now we do an insert, a heap insert. We know and love heap inserts. Here's our heap insert. As long as we've got room, we just add it to the end of the array and we do a fix-up. That's what we started with. 1, 2, 3, 4, 5, 6, 7. I explained to you a number of times how you just add a new element and you heapify, fix up, so that you check with your parents to make sure that you are not bigger than any parent or grandparent, etc. So we add the element, we increase the number of elements by 1 because we've got a new element IT, we stick him on the array and we do a heapify or a fix up and we're finished. It was that easy. My goodness gracious, it sounded like it was going to be hard, but the heap actually is quite a simple thing. Okay, so we're just now inserting using a heap strategy. And just realise what's going on here. We've got the same array in all 3 implementations. It's just that we're shuffling them around a bit. One, we don't care the order, the sloppy. The other one, we're being really fussy, and that's the ordered one. And this one, the heap, is we're sort of a little bit careful where we put things, and we always know, with our heap, where the top element is. And there's only enough order in a heap to give us the top element. It isn't over the top order in the sense of a fully ordered array, which is what the second solution was, the OA solution. That's a ridiculous amount of order. I just want the top element. I don't want all the other n-1s. I just want the top element at any point in time. And that's what the heap gives us. It gives us the top element, and it doesn't care about the rest. There's partial order in there, but it makes sure that after every operation, every delete or pop, that it restores the heap so that it can give you the next time another heap, another max in log n time. So here's the delete max, and what the delete max do, it gives you retval is items 1, 1, 1. And you know that with all this X stuff I did here, 0 is a hash or a -999, position 1 is the top. Dead easy. That's where it is. I can get it instantly, constant time. Well, it's not quite that simple. I've got to do a fix down. Because I've taken the root out, I've got to then put the last item, the item at n items, the last one in the array, I've got to put that in the root, and I've got to heapify. I've got to fix down to fix it all up, and that's going to be log. But you've seen this stuff before. You'll be doing it in the exercises. That's why I've really pushed on the exercises. Use fix down or fix up a lot so that you really get a sense of what it is and what it's doing and how simple it is, how robust. So this is just fix down being called to fix up the heap after you've removed the root. And the exempt is exactly the same.